as you can see, the picture over there is the picture behind our university from the mountains you can see. But where I have an office right next to Professor Liu, Chen Ching's. But for the last year or so, I've been, my wife and I have been in the district here in Washington, and I'm on detail here at the Department of Energy, working with Phil and others. So I haven't been back there very often in the last year or so. But anyway, I wanted to, it's really nice to come to an event where people are lamenting the fact that people are retiring and they're asking them to stay involved and so on, because mostly where I come from, you get the feeling that people are waiting to get out, that you get out of the way so they can get the bigger offices. And I think in being late in the afternoon now and having missed the morning sessions, I realized that we're repeating a lot of things here. I had intended this presentation to be kind of answering the question of, yes, Arun and Jim invented this new thing, and is it good for anything or not? And almost everywhere you go, they ask, what are you doing with it, right? And so, of course, if you read the writings of Jim and Arun, they all anticipated almost all of the things we're doing, but there's a lot of things they anticipated we're not yet doing. And so the question is, what is the stage of the art? How far have we come? How much is it left? What are the big challenges? And so on in getting the promise of applications here. Now, I'm not going to cover a lot of this stuff here in the short amount of time, but much has been said already on it. So let me go. So what is the state of the art? And I'm looking at it from controls point of view, from the control center point of view. And as you see, the SCADA EMS system that we're all used to are mainly doing a lot of monitoring, straight monitoring, of the real-time data that's coming in, whether that be in forms of visualization or alarming or whatever. And then the EMS part is also more analytical techniques that are used to parse this data into better information for guidance of the operator, right? So whether you do state estimation, contingency analysis, you can even maybe have some remedial actions set up for the operator and so on. But so far I haven't said anything about control, right? The control is expected to be done by the human operator. So what is the closed loop control that we have? And the only thing really we do that involves the control center is load following, or APC, right? In some countries, they're now doing voltage control, China, Europe, and so on, regional voltage control. That's with the calculations being done at the control center, and so on. So, but for any kind of fast controls or protection, we're dependent on mainly localized systems, right? So that was, I think several people have mentioned that the big expectation that comes out of the PMUs would be in that category where you can do much wider types of control automatically and fast. Okay, so the first issue then is that comes into play is that you have the communications now involved in the control system. So the communication delays may get in the way, or at least has to be taken into account in designing the control system. And right now, the way things are being done, and there's a lot of PMUs going in, in not just in the US, but all over the world. And basically, almost all of the data is being hierarchically channeled up to a central place. So whether you centralize all the data within the substation to a PDC, up from the PDC to a local control center, up from there to the balancing authority, up from there to a reliability coordinator. So it's all in a hierarchical fashion, and the general feeling is that this is not going to be good enough for closed loop fast control. This will be perfectly fine for doing any of the other things that we do in the control center, especially the human operator-based things, but not for closed loop control. And that's why I think you see that that a lot of people are looking at the communications control interface to determine whether things can be made to work. So the thinking is that you will do something like a networked communication to try and get around the problem of sending data all the way up to the reliability control coordinator and down all the way down to the substation in another area. After all, we're trying to do wide area control. And so if the substations required in the wide area control are far enough apart, they'll have to go through several things. And I know Eric mentioned the WEC system, and it is true that that WEC is gathering data using the Harris communication systems, which has very low latency. But the low latency is from the PDC of the individual control centers to WEC control center. So if you want to do a control that takes the PDC, the PMU data from a substation up to WEC and back down to a substation where you're doing a fax device or something in another part of WEC, you'll have to go through all the switches, and there may be up to 5 to 10 switches in between. And our experience with communication simulations is that the delays are all in the switches, and we're not going to meet the 100 and 120 milliseconds things that Eric was talking about. So, so what are the issues? The wide area monitoring, the biggest issue in visualizing with wide area monitoring is that the data is voluminous and it comes fast. So there's a lot of effort going on now in how do you present that to the operator, right? So that's the first set of things that the PMUs are good for. One of the applications that has become quite common actually today is that oscillation detection has become very feasible. So this is probably close to some closed loop control. If you can do that oscillation detection relatively quickly, you can start closing the loop in getting the damping up in the generating plants to get the oscillation down. Now, nobody has tried that yet, but I think the technology is getting closer and closer to try a closed loop control to dampen oscillations. So the PMU-based control that we're talking about right now in the fast space is really very much still in the conceptual stages. I mean, apart from some special protection schemes that can be done, we're not getting some techniques where some analysis is done at a fast pace and then closing the loop with that. So that remains a big challenge. Things that people are working, and yesterday, actually Joe was presenting something at DOE about the number of PMUs and the question of what is the right number of PMUs in the system. And of course, the thing that we kind of disagreed on is, is that I think the game is changing. You know, if 10 years ago people thought if you had a half a dozen, it'd be great. You know, now people are saying thousands of PMUs, you know, tens of thousands of PMUs, if not hundreds of thousands of PMUs. So I don't know. I mean, if you can think of better and better applications, the ante goes up, right? But one of the things that is coming along now is that a lot of countries are looking at observability as the criteria, and observability in the state estimation sense, right? So if you want to do that, that automatically sets a number where you get observability and enough redundancy to be able to do state estimation with PMU alone. And of course, the first papers written on this subject, again, was Arun and Jim, and pointing out the very obvious fact that if you have currents and voltages, you get a linear set of equations, and then you don't need to worry about the convergence of the state estimator. Now, I'll tell a little story here, because I ended up working very early on state estimators. Now, the first work on state estimators was done at AEP about the same time as Arun was actually there, and I don't know how much Arun was involved with that, but there was a whole group of people at AEP looking at state estimators, and except of course the AEP people didn't call it the state estimator; they called it the online power flow, and there are papers written from that thing, and I was a graduate student at that time, and so reading those papers rather with great interest, and the online power flow couldn't converge using the power flow algorithm.
It still doesn't.
And it still doesn't.
It still doesn't.
No, it doesn't. And that's why we had to find a different algorithm, which happened to occur because Fred Schweppe came and spent some time at AEP, and he recognized it and formulated it as a state estimation problem. However, what maybe most people don't know is that AEP actually went ahead and implemented a state estimator that did not use all the measurements that Fred Schweppe was using. They implemented a state estimator which only used the power flow measurements on the P and Q measurements on the lines. And it came to be known as a lines-only state estimator. In the meantime, the commercial vendors started putting together a Fred Schweppe type state estimator, which is sort of like the state estimator used today. And I happened to be working at Control Data at the time, and we were one of the first ones. And there's a long story about the antecedents of the commercial state estimator, where Systems Control did the first one, Control Data, then built another one, Systems Control, finished, formed, people split off from Systems Control, and people like CIGRE formed ESCA company, which had the same one. So there were like 3 or 4 of these things that looked almost identical, but were commercially competing with each other. And it took about I think once the commercial ones came out, AEP found that it's kind of hard to keep up their own one painstakingly, and so they switched. So I'm going to show you, so why do a state estimator with PMUs? The reason is that you can do it much faster. See, when we actually designed these state estimators so long ago, the thought was that it will come in fast enough to be able to design remedial action schemes, and the operator could do something with the contingency analysis results. But at the time, the fastest state estimators were about 15 minutes apart, and now they're probably about a minute apart. And even then, it can be made much faster because of the time skews that the present SCADA system has. And so the PMU has the ability now the PMU-based data estimator to give you a much more accurate answer many times a second. And now you can think of controls that are based not on the raw data, but on state estimated data with other things thrown in. And that's what the promise of this, of the state estimator is. So to finish up, I'm going to not go to any more slides. There's about 3 of these state estimators being tested right now under experimental. The first one, of course, you probably have already heard of it because it came out of Virginia Tech and it's being tried out in Dominion, and many of the people in this room, I'm sure, are very involved with that. There's another, the other one is the Georgia Tech one, which is being tried out in New York State and Virgin Islands, and that one is actually distributed state estimator, very different from one. And then we have one at Washington State where it's kind of half and half. You're doing some of the calculations at the substation level and then putting it together. And we're trying to, with Alstom, trying to do this with Vahid Madani's system in PG&E. So about 2 months ago, Arun asked me to come down to Virginia Tech in Blacksburg to talk about something like this, and I was to explain to them our state estimator and pointing out the differences and so on and so forth. And Arun assured me at that point that the Virginia Tech state estimator is significantly better than any of the others. Thank you.